Now talk about application of Gauss's law. Now Gauss's law is very helpful. It can be used to determine electric fields. Now to use Gauss's law, two conditions have to be satisfied. One, the charge has to be distributed symmetrically. And number two, the angle between electric field and the small area vector ds vector is pi or 0, that is E vector and ds vector are parallel, or theta is pi by 2. They are perpendicular. So if these two conditions are satisfied, then we can use Gauss's law to determine electric field. So let us do a first example of application. So say you are given a sphere of radius r, and this sphere has charge q, capital Q. So this sphere is conducting surface, and therefore this charge is distributed uniformly. So first condition is satisfied. So we need to find electric field at a distance a. From the center of the sphere. So let us see this in the figure. So you have two spheres. One sphere is red. So this red is the sphere. So this radius is r, and you need to find electric field at distance a from the sphere. So this is distance a. So purple line is the distance a from the center of the sphere, and the sphere has radius r. So this red sphere is uniformly charged. So first condition is satisfied. So according to Gauss's law, the flux through the sphere with radius a is q over E0. Now flux does not depend upon the radius, so it is same as it is on the red sphere as it is on the purple sphere. So now we want to calculate flux through direct calculation. So the formula for flux is surface integral of E vector dot ds vector. So you have E ds cos theta, and we will show that E and ds are parallel, theta is 0. So you take E out because E does not depend upon the surface area. The surface area of the sphere with radius a is pi a square. So flux you get is E times pi a square. So we have also calculated flux as q over E0. Now we already know that the flux is also calculated as E times 4 pi a square. So you equate these two, and you get electric field as q over 4 pi a square E0. So notice that the formula shows us as if all the charge is concentrated at the center of the sphere. Now notice that in this case it does not matter whether the red sphere which is inside is either hollow or solid. The answer will still be the same. Now we just want to talk about that the second condition is satisfied for the Gauss's law. That is theta is 0 between electric field and the surface vector we are talking about. So notice that electric field is coming out like this. And the small surface area is given on the sphere of radius a. So uniform distance a from the center is just a sphere. This small area is ds, and perpendicular to this area we have the ds vector, and you can clearly see that the electric field and the area vector have angle 0 between them. Now we talk about inside the sphere. Now in the first case it did not matter whether the sphere was hollow or solid, but in the second case if you are going to calculate electric field inside the sphere has to be solid. In case of a hollow sphere, the electric field is 0. So why is electric field 0? The electric field is 0 precisely because of superposition principle. So there is uniformly charged sphere around it, and all particles will try to pull each other out, and therefore all the electric field will cancel each other in case of a hollow sphere. But for a solid sphere, we can talk about electric field inside it. So now in this case, we have taken a sphere which is inside the solid sphere of radius r. So we have a sphere of radius a. So the flux calculation remains as before, as in the previous case. The flux is for sphere of radius a is integral of E vector dot ds vector, and just like in previous case, the flux comes out to be E times 4 pi a square. So this is the flux associated with sphere of radius a, and now the sphere of radius a is inside the sphere of radius r, and both r and a are solid spheres. So the Gauss's law says that the flux will be equal to q over E0. Now I'm using small q. Now this small q is charge on the inner sphere. So since this is a solid sphere and we assume it to be a conducting sphere, this charge is distributed symmetrically. So first condition of Gauss's law is satisfied. That is q divided by the volume of the sphere is equal to capital Q divided by the volume of the bigger sphere. So the charge density is the same. So this implies Q is equal to A over R cube times Q, because 4 by 3 pi cancel out. So now we have two equations, 1 and 2. We plug them equal to each other. 1 equals to 2, and then we plug in the value of small q. So from equation 1, we have flux is equal to E times 4 pi a square, and this is equal to q over epsilon 0. Now you divide both sides by 4 pi a square. You get 1 over 4 pi epsilon 0 times 1 over a square times q. So basically E becomes q over 4 pi a square epsilon 0. So instead of small q, we will write capital Q times a over r cube. Now we do the cancellation of a square, and we get q over 4 pi epsilon 0 times a over r cube as the electric field. Now this is the case when A lies inside the solid sphere R. Notice that electric field will be 0 if the sphere is hollow. So we are always talking about a solid sphere in this case.